Hello, grade 11s. Right, we're going to continue with vectors. Right, so today we're going to look at closed vector diagrams. A closed vector diagram is a set of vectors drawn on the Cartesian plane using the tail-to-head method, and that has a resultant with a magnitude of 0. This means that if the first vector starts at the origin, the last vector drawn must end at the origin. The vectors form a closed polygon, no matter how many of them are drawn. Here are a few examples of closed vector diagrams. So this is one example. Right. In this case, there were 3 force vectors. When drawn tail to head with the first force starting at the origin, the last force drawn ends at the origin. The resultant would have a magnitude of 0. The resultant is drawn from the tail of the first vector to the head of the final vector. In the diagram below, there are 4 vectors that also form a closed vector diagram. Here they are. In this case, with 4 vectors, the shape is a 4-sided polygon. Any polygon made of vectors drawn tail to head will be a closed vector diagram because a polygon has no gaps. Using Pythagoras' theorem to find magnitude, if we wanted to know the resultant of the 3 blue vectors and the 3 red vectors in figure 1.2, we can use the resultant vectors in the x and y directions to determine this. The black arrow represents the resultant of the vectors r of x and r of y. We can find the magnitude of this vector using the theorem of Pythagoras because 3 vectors form a right-angled triangle. If we had drawn the vectors to scale, we would also be able to measure the magnitude of the resultant as well. What we've actually sketched out already is our approach to find the resultant of many vectors using components. So remember this example when we get there a little later. Here's an example. The force vectors in figure 1.2 have the following magnitude: 1 Newton, 1 Newton, 2 Newton for the blue ones, and 2 Newton, 2 Newton, 1.5 for the red ones. Determine the magnitude of the resultant. The resultant of the vectors parallel to the y-axis is found by adding the magnitudes of 3 vectors because they all point in the same direction. The answer is 4 Newton in the positive y direction. The resultant of the vectors parallel to the x-axis is found by adding the magnitudes of 3 vectors because they all point in the same direction. The answer is 5.5 in the positive x direction. We have a right-angled triangle. We also know the length of 2 of the sides. Using Pythagoras, we can find the length of the third side. From what we know about the resultant vector, this length will be the magnitude of the resultant vector. So that is 6.8 Newton. Note, we did not determine the resultant vector in the worked example above because we only determined the magnitude. A vector needs a magnitude and a direction. We did not determine the direction of the resultant vector. Now let's look at graphical methods. Graphical techniques. In grade 10, we learned how to add vectors in one dimension graphically. We can expand these ideas to include vectors in 2 dimensions. Now the following worked example shows this. Given 2 vectors, r of y is 4n in the positive y direction and r of x equals to 3n in the positive x direction. Use the tail to head method to find the resultant of these vectors graphically. Now, the vectors we have do not have very big magnitude, so we can choose simple scales. We can use 1 1:1 as our scale for the drawing. Then we draw axis that the vector diagram should fit in. The largest vector has length 4 Newton, and both vectors are in the positive direction. So we can draw axis from the origin to 5 and expect the vectors to fit. The magnitude of Rx is 3 Newton, so the arrow we need to draw must be 3 centimeters long. The arrow must point in the positive X direction. That's the arrow. Step number 3, the length of Ry is 4 Newton. So the arrow we need to draw must be 4 centimeters long. The arrow must point in the positive Y direction. The important fact to note is that we are implementing the head to tail method. So the vector must start at the end of Rx, right? Here we go. And then the resultant vector is the vector from the tail of the first vector we drew directly to the head of the last vector we drew. This means we need to draw a vector from the tail of Rx to the head of Ry. We are solving the problem graphically, so we now need to measure the magnitude of the vector and use the scale we chose to convert our answer from the diagram to actual result. In the last diagram, the result is 5 centimeters long. Therefore, the magnitude of the vector is 5 Newton. The direction of the resultant theta we need to measure from the diagram using a protractor. The angle that the vector makes with the x-axis is 53 degrees. Therefore, R is 5 Newton at 53 degrees from the positive x direction. In the case where you have to for example, you would first calculate Ry from all the vectors parallel to the y-axis, and then Rx from all the vectors parallel to the x-axis. After that, you apply the same procedure as in the previous worked examples to get the final resultant. Now, on example number 6, finding the magnitude of the resultant in 2 dimensions graphically. Given the following 3 force vectors, right, determine the resultant force. Force number 1 is 3.4 Newton in the positive x, 4 in the positive x, and then 3 in the negative y. First, we determine the resultant of all the vectors that are parallel to the x-axis. There are 2 vectors, f1 and f2, so we need to add. We do this using the tail to head method for collinear vectors. The single vector Rx that would give us the same outcome is this black one. There is only one vector in the y direction, f3, therefore Ry is equal to f3. The vectors we have do not have very big magnitude, so we can choose simple scales. We can use 1:1. Then we draw axes that the diagram should fit in. The longest vector that has length 7.4 Newton. We need our axis to extend just further than the vectors aligned with each axis. Our axis need to start at the origin and go beyond 7.4 in the positive x direction and further than 3 Newton in the negative y direction. Our scale choice of 1:1 means that our axis actually needs to extend 7.4 centimeters in the positive x direction and further than 3 centimeters in the negative y direction. So that's that. Then draw R of x. The magnitude of R of x is 7.4. So the arrow we need to draw must be 7.4 centimeters long. The arrow must point in the positive x direction. That's the blue arrow. The magnitude of the Ry is 3 Newton. So the arrow we need to draw must be 3 centimeters long. The arrow must point in the negative y direction. The important fact to note is that we are implementing the head to tail method, so the vector must start at the end of R of X. The resultant vector is the vector from the tail of the first vector we drew directly to the head of the last vector we drew. This means we need to draw a vector from the tail of Rx to the head of Ry. We are solving the problem graphically, so we now need to measure the magnitude of the vector and use the scale we chose to convert our answer from the diagram to the actual results. In the last diagram, the result R is 8 centimeters long. Therefore, the magnitude of the vector is 8 Newton. The direction of the resultant we need to measure from the diagram using a protractor. The angle that the vector makes with the axis is 22, right? So R is 8 Newton at negative 22 from the positive x direction. Okay, now we are given 4 vectors. Again, you need to use the very same logic, right, to find the answer. Okay. A number of tugboats are trying to maneuver a submarine in the harbor, but they are not working as a team. Each tugboat is exerting a different force on the submarine. Now, given that, okay, to use the graphical method of finding the resultant, we need to work in the same units. Strictly speaking, in this problem, all the vectors are in Newtons, but they have different vectors which will affect the choice of scale. These need to take into account. The simplest approach is to convert them all to a consistent unit and factor. We could use kilonewton or Newton. The choice does not matter. We will choose kilonewton. Remember that kilo represents a factor of times 10 to the 3. Okay. Alrighty. I do all of that, you do all of that, and then the answer is 4.7 kilonewton at negative 44 degrees from the positive x direction. Now let's look at the algebraic methods. In grade 10, you learned about addition and subtraction of vectors in one dimension. The following examples provides a refresher of the concepts. A force of 5 Newton to the right is applied to a crate. A second force of 2 Newton to the left is also applied to the crate. Calculate algebraically the resultant of the forces applied to the crate. A simple sketch will help us understand the problem. Now remember that force is a vector. Since the forces act along a straight line, meaning the x direction, we can use the algebraic technique of vector addition. Choose the positive direction to be the right. This means that the negative direction is the left. Rewriting the problem using the choice of a positive direction gives us a force of 5 Newton in the positive x direction and force of 2 Newton in the negative x direction being applied to the crate. Now, if we add them up, we get 3. Remember that in this case, a positive force means that to the right, 3 Newton to the right. We can now expand on this work to include vectors in 2 dimensions. A force of 30 Newton in the positive x direction acts simultaneously at the same time to a force of 30 Newton in the positive y direction. Calculate the magnitude of the resultant force. As before, the rough sketch looks as follows, right? So that's how it looks. Note that the triangle formed by the 2 force vectors and the resultant vector is a right-angled triangle. We can thus use the theorem of Pythagoras to determine the length of the resultant. Let R represent the length of the resultant vector. Then, using Pythag, we get 50 Newton as the answer. Now, direction. For 2-dimensional vectors, we have only covered finding the magnitude of vectors algebraically. We also need to know the direction. For vectors in 1 dimension, this was simple. We chose a positive direction and then the resultant was either in the positive or in negative direction. In grade 10, you learned about the different ways to specify direction. We will now look at using trigonometry to determine the direction of the resultant vector. We can use simple trigonometric identities to calculate the direction. We can calculate the direction of the resultant in the previous worked example. Now, we determine the magnitude of the resultant vector and we got 50. Now, to determine the direction of the resultant force, we calculate the angle alpha between the resultant force vector and the positive x-axis by using simple trick. Tan alpha is equal to the opposite side over the adjacent side. So that's 30 over 40. And then you take inverse tan 0.75, which is 36.87 degrees. The resultant force is then 50 Newton at 36.9 to the positive x direction. All right, folks, you can try these exercises on your own, right? Then in the next video, we'll look at components of vectors. Thank you so much. Hey, please don't forget to like the video, subscribe. Please subscribe, like the video.